I'm going to walk through the problem that we were faced with in our practice exam. It included a non-isothermal batch reactor. It gave us two differential equations, so we needed to eventually plot the concentration versus the time as well as the temperature versus the time using the Euler method and the predictor-corrector method, which is kind of like a modified Euler method, I guess. So in order of this, to do this, it was defined that we needed to use a step size, or a change in t, of 0.1 hours. And we used that in the modified Euler and predictor-corrector method to get our final plots. So we were asked to look at the change in concentration and change in temperature as time progressed in a non-isothermal batch reactor. So we were given two equations that both were related to the temperature and the concentration, but both of them were differentials, but they didn't have a variable time in their equation. So we started by, of course, just displaying what part we were, so we know where we were, the classic clear CLC close. So we decided to use the Euler method first, and so we had a step size of 0.1. So our t-values range from 0 to 5 with that step size here. And we wanted to make sure that we had an initial value of 1 for concentration, because that's what it was stated, as well as 16 degrees Celsius for our temperature initial. So first we did a for loop with the I ranging from 1 to the length of t, which we have here, minus 1. So we started with the concentration at I plus the step size times the differential equation there. So that's the classic Euler method. And since it's a for loop, we have the c equals I plus 1, so they can reiterate over and over again. And the same thing goes for the temperature. We decided to run these together because you could, and it made sense. It made things a little easier for us. So next, when we wanted to move on to the prediction corrector method, we had to set our initial CPC, which is concentration predictor correction method. Initial is equal to 1, and then the TBC of 1 is equal to 16. So we did another for loop, which is the I ranges from 1 to the length of t minus 1. And so first we did like the same Euler method that we had above here to find what our C predictor value was. And once we found that, we decided that it's pretty much like a modified Euler, but you take the initial point here plus the step size over 2 times the averages of your two new slopes. So, not two new slopes, but the slope that you found in the Euler and the one that you find now. So you take the average of it and it gets a better value. And so then it'll run through multiple times until you get to the final length of t minus 1, and it will end. So here we had the statement figure, because you always want to do that before you plot things. And because we wanted to have 6 different graphs, we had the graph of the two methods in one figure, so one for concentration, one for temperature, and then the plot of the absolute difference. So we did that absolute difference for the absolute difference for temperature as well as the absolute difference for concentration. So you can see that if we run these, we have 6 different graphs all in one figure. And you can see here that the way we did this was by using the subplot. Here. So you notice that we had 3 rows. Here, let's see if we can squeeze this over. 3 rows, 2 columns, and then the first figure that we did was the concentration of the reactor compared with time. This is our first plot, which you can see right here. And for our second plot, which we reference, is the temperature of the reactor with the time. So it's over here. So it goes from 1, 2, 3, 4, 5, 6. So we had 3, 2, 1, and then we called out specifically which plot we wanted in each space as we moved down this. So for part B, we wanted to use a while loop, and we're asked to use a while loop to find the required change in time, like the step size that makes the difference between the Euler and predictor corrector method below a certain standard. So what we did is we started with the classic clear CLC close, and set our x equal to 1, our step size of 1 equal to 0.1, and then our h of x equal to 0.03. And our h of x is our error, and I'll talk about it later, but the reason we use 0.03 is after we fiddled around with it for a while. We originally had it at 1, but when we finally got the graph to work, there was a big gap, and the highest error that we found was about 0.025-ish, so we didn't want to, it didn't make sense to have our initial value of 1. So while our error is greater than 0.001, which is what we wanted to do, we took steps of x equals to x, and then your dt, so your step size of x plus 1 equals the dt of x minus 0.001. Which was what you guys gave us is how much we wanted to reduce each time as we moved throughout the while loop. So once again, we have our t equals 0. We wanted to use dt of x here because it's changing as we move through from 0 to dt of x of 5. And then our concentration initial of 1 is equal to 1. Our temperature of 1 is equal to 16. And then inside of there we had to do a for loop for the original Euler method that we just copied and pasted from our other script. And then we then did the initial values of the predictor correction method, and then we copied and pasted our other predictor correction method for loop from over there. And so it's stated that, so it'll keep running through that until you get the values that you're looking for each time. And so we wanted to make sure that h of x plus 1 equals the sums of the absolute value of the Euler minus the predictor over the predictor, which is what we were looking for. And so that's how you can find the error. And then so in order to keep tabs of how many times we were iterating, that's why we have the x equals x plus 1. So like, once we get through here and it has finally ran its loop, that's why we display dt of x. So that shows the time interval that we iterated. And so after that we plotted the time step by the error in red dots. You can see here. So this is the final graph that we came up with, and you can see that as the time step increases, so does the error. So basically what it's saying, like the smaller steps you take between your the smaller the steps are that you take between your guesses, the more accurate your estimate becomes.